just like start with reminding you where we left off yesterday. So after an extended discussion of Harlow's theorem, I defined a particular code in 2D CFTs. Okay, the output is the code was in the Hilbert space of two different CFTs, which I'll call L and R, despite protestations from the audience. And what I proved was that every state in the code looks like the following. So there's a sum over the primaries of the CFT. Sorry, it's a it's a sum over primaries of the CFT of states, each of a state which is in the descendants of the left CFT and the right CFT, but with the same primary. Okay, and there is this quantity square root PO, which is the probability of the particular primary O. Okay.
So just to ask you, so there was this parameter epsilon when you first started, but it's not really there in the final code subspace.
Yeah, that was it. That's just some.
Yeah, right?
Yeah, exactly. The final code subspace is this. Okay, I just kind of wanted to give a nice localish definition of it. Yeah. Okay. So one step that I skipped yesterday is that this form implies the following: that for any state in the code subspace, the entanglement entropy of that state reduced to the left CFT, okay, looks like the following. It looks like a Shannon entropy for the probability distribution over primaries, plus an average of the the entanglement entropies of all these states on the descendants. Okay, so there's a descendant entanglement entropy, and there's a Shannon entropy. Okay, anyway, for now let me just focus on the Shannon entropy. Okay, so I will do everything now in terms of, for a while I'll just talk about classical probability distributions, and I'll come back to quantum mechanics later. Okay, yeah. So
can you explain the second part?
This
Descendant entanglement.
This one? How do I? Yeah. So basic point is that because your state looks like this, your reduced density matrix on the left CFT kind of looks like this. Square root sorry, PO rho O P O prime rho O prime and so on. It's like it's block diagonal. Okay, each block corresponds to a single primary. Okay, and when you take trace rho log rho, okay, you get you basically get a part which is just the and all these rho O's are normalized so that traces are 1. So when you take trace rho L log rho L, you get basically minus some PO log PO. Okay, and then like maybe I'll just be a little more explicit. Okay, this is equal to minus sum over O trace PO rho O log of PO rho O, right? I'm just plugging in the block diagonal form here, but then you notice that this guy can be written as log PO times the identity operator plus log rho O, right? And this identity part and then trace of rho O is 1, so the identity part gives you a Shannon, and then here you get rho O log rho O but weighted by PO, which is exactly this piece here. Okay? Yeah.
So this part is just true, it follows from.
Yeah, it's literally this is the full calculation. Yeah.
That's descendant entanglement you said, right?
Yeah, that's the entanglement of descendants within each primary sector. Okay? Good. Now the point is that there is no area operator here, information theoretic area again. Okay? So to create an area operator, the one nice thing to do is coarse grain. Okay? And I will coarse grain the Shannon entropy.
Sorry, so the reason there is no area operator is because, say it again.
The reason there was no area operator is that what the area operator was it was basically measuring the sort of irreducible entanglement that your code operators cannot destroy, but this code is so big it contains factorized states. Okay. Yeah. So this was the fundamental reason. So of course you could be like, okay, make a better code, like just grow up. But I think there's some physics in just not making a better code first.
And I also think that this entanglement, if there were area operator, there would be an additional term here.
Yes, then there would be then there would be some what do you say, sum over PO f of O, where f of O is independent of the state. That's an area operator, because because the state appears only once. In all of these terms, the state information appears multiple times.
So in the previous case, if I think of this as a code subspace inside the original space, it had an orthogonal part
Yeah.
in which the chi lived.
Right? It was not orthogonal part. It was different degrees of freedom which was not
Yeah,
touched.
different degrees of freedom.
Here basically the point is that
all the degrees of freedom are encompassed.
Yeah,
So
yeah.
that's-
yeah,
And not orthogonal, direct product piece. Yeah.
yeah, yeah.
Ronak, the way you set it up, I thought one obvious way to get an area term would be that you start with some state, your analog of this epsilon independent state, which entangle all the primaries with each other. Right? Then the set of descendants you allow in your code is only some low-lying primaries descendants. And
Sure.
then there would still be the entanglement of the higher dimension primaries, which would be kind of irreducible. Because the low line wouldn't change it. I thought that would be the kind of analog.
In fact, I think there are also, as we'll see, like what I will reproduce is the geometric area. At least like there are good guesses in the literature that what I'll have is the geometric area, because the idea is that, see, descendant stuff is boundary graviton stuff. Okay, it's close to the boundary. Okay, so you have this boundary gravitons kind of live here. Okay, so they should not be part of the area operator. Any descendant entanglement should just be part of bulk entanglement. Okay, and in some sense, all the part that is kind of what is the area? Area is something that's shared between the two sides, right? And so basically, the part that's going to be area is going to be coming from just the probability distribution over primaries, because the primaries are shared between the two sides.
Just, I mean, continue with what Sandeep was saying. You could imagine that you aren't going to touch the primary primaries above a certain dimension,
You could do it. We could do that, yeah.
and then that would give you a.
No, it would not.
No, but
The above.
it was about the degrees of freedom, right? So the code subspace, as I said, there was a code subspace and then there was a factor.
Yeah.
Because the Fox space interpretation. Now in 2D CFT, you're just directly specifying the spectrum as opposed to degrees of freedom.
Yeah.
Meaning there's no direct product structure.
Yeah.
So if you just cut it off here, that is just some separate thing up,
Yeah.
right?
No, there's no direct product structure.
Yeah.
This is a direct sum.
Yeah.
Expressed as a direct
That's
sum.
what I was confused about.
Yeah. Thank you. That
Right.
that's a very good way of explaining
Okay,
it.
good point. Okay. Thank you.
Yeah.
Yes, sir.
Okay. So then, oh yeah, and let me just go through the thing, and then you'll hopefully find it more convincing that the area operator is roughly what I'm going to show you. Okay. So now, so I will kind of consider this as a probability Shannon entropy, a classical entropy over a classical set, forgetting about quantum mechanics for a while. Okay, because, and so what I'll do is there's a classical set of O's, okay, which as I'm equivocating between this being an abstract space and this being an energy direction, which is fine. And I will I have defined a set of bin functions f alpha of O. Okay, it's a function because it has a dependence on O, and alpha is basically like a bin number. So roughly speaking, it's telling you where the peak of this bin function is. Okay, and I will demand that it's a partition of unity. Okay, I have put a general measure here, which means I might allow alpha to be like continuous or discrete or anything. Okay, but however I integrate over alpha, at fixed O, it should always sum to 1.
So can I think that if your previous O was like a delta function, you just smear it out. So instead of O, you just collect.
Yeah, I'm collecting a bunch of primaries under a single alpha. Yeah.
What O would have
Yeah.
contributed, you replace it by this.
Yeah, but we'll do it like slowly.
Yeah, but that's okay.
Yeah.
So e to the power minus x square, x minus alpha, the whole thing square. X
Yeah, roughly speaking, that will do the job. Yeah.
e to the
In fact,
power
yeah,
x
when
of pi.
whenever I do a calculation, that's the thing I put in. I just put a Gaussian.
Gaussian, and then integrating that over all alpha independent of x gives you.
Yeah, exactly. Cool.
X is
Oh.
your dimension.
Yeah, H, E, whatever you want to call it. Yeah. Okay. So no, you integrate it over all alpha, you get a number for every O.
You get a number for every x.
Yeah.
Independent of x.
Yeah, and you can make
That's
it
what
one
you
way.
want,
Yeah,
right?
that's right. Cool. So anyway, you can of course put Gaussians. You can try to put if you are a fancy boy, you can put more clever functions if you want. I am a Gaussian man myself. Anyway, so the point is that because I demanded that be a partition of unity, you can basically give this a probabilistic interpretation, which is that if you give me a primary O, I will put it into bin alpha with the probability of f alpha of O. Okay. Therefore, I can think of probability f alpha of O as a conditional probability. It's f of alpha given O. Sorry, it's probability of alpha given O. Okay. And therefore, if I multiply PO and P of alpha given O, I get P of alpha comma O, which is a joint probability distribution. Okay. Good. Now, let me just define a couple more things. I will define n alpha as the number of O's included within each f alpha. Okay. Why did I put an equal one here? It's not equal to 1, it will be big. Okay. And P alpha I am going to define as like the marginal probability when I trace out O. Okay. It's like conditional psi. It's basically just the total probability of having bin alpha. Okay. Good. So now, what I care about again is H of O, which is minus sum over O, PO log PO. Okay. And now you can add and subtract a bunch of things. I can rewrite it as P alpha log P alpha okay, P alpha over O log of it should be H of O given alpha. So here you see that P alpha log P alpha gets cancelled with this log P alpha here, because when you sum this guy over O, I just get P alpha. Okay. So now, but now I have this P alpha O log P alpha O. I have to get rid of that. I'm going to get rid of that by P of alpha O log of P of alpha O by PO. Okay.
Right. Yeah, you started with PO log PO, and what formula are you using after that to write PO? And is it this formula?
Oh, which formula?
You're substituting PO in terms of other things, right?
No, I'm going to add and subtract a bunch. I'm adding and subtracting a bunch of things.
Oh, okay.
Okay. So now look. So now what I've done here is, if I look at the denominator here, it's just minus PO log PO, because when I integrate this guy over alpha, I get PO. Okay. So that's the original term. This guy cancels with this guy cancels with this guy. Okay. Just adding and subtracting. The reason I did all this is that what I have here is the expectation value of the log of base theorem. Okay. This can be written as the Shannon entropy of alpha plus the Shannon entropy of O given alpha. So this is the average uncertainty in O once I tell you alpha, minus the Shannon entropy of alpha given O, which is the average uncertainty in the bin given the primary. Okay, these are the three terms here. Okay. Yeah, I just went through this to make sure to emphasize that this is completely non-mysterious. Okay.
This is completely
Mysterious.
So second term is what do you mean with HO slash alpha?
It's a conditional entropy. It's like the amount of uncertainty you have about the primary if I give you the bin. Okay. And this is the amount of uncertainty about the bin if I give you the primary. Okay. if you're not comfortable with conditional entropies, that won't be important. We can just look at these formulas up here.
And just to make sure, integral of over d mu alpha p alpha 0 is p0.
Yeah, that's right. Because of this condition. Because yeah. So now good. So H alpha now is just the Shannon entropy over of uncertainty in alpha, which we would want. Like even in Harlow's theorem, there was a Shannon entropy in the uncertainty over the alpha sector there. Okay.
So here you are expressing that P0 log P0, PO log PO quantity because the code is still the same. Right?
The code is still the same. I'm
expressing in some other.
Yeah, I'm trying to do a coarse graining. I'm trying to coarse grain the entropy.
Yeah. Okay.
Okay, which I
Can you explain second line again? I don't understand tensor.
because see it's you could just consider say the denominator here. Okay, it's plus of d mu alpha p alpha o log p alpha. Okay, but when you sum over o of p alpha o, I get exactly p alpha, right? So that exactly, this is a plus, that's a minus, they cancel exactly. The p alpha o's obviously cancel because literally the same expression, and here I get minus log po, and then log po does not depend on alpha. So when I integrate this over alpha, I go back here, I notice that p alpha o is just po times f alpha o. F alpha integrates to 1, so this just becomes po log po, which is what I wanted in the original. Okay, but I'm just saying that this Bayes theorem can be used for coarse graining, which was something which made me very happy when I understood. Okay. Yeah.
Just to make sure I'm understanding it correctly. You had this PO originally. Now we could imagine one possible answer for PO would be P alpha. Okay. And this P alpha is like, okay, I can think of as like a basis for all possible distributions PO.
I completely confused. What P? One possible answer for PO is P alpha.
So you want to assign a probability for every H.
Yeah.
That's in your initial formula. That's all. That
Yeah.
is. Now, P alpha assigns a probability for every H.
Yeah. But in general, a different set of H, because alpha could be a continuous set even though the underlying set
Alpha
is.
thinking of just as a number, as a link.
Yeah.
But it assigns a probability for every H because it's function of
Yeah,
P
yeah.
alpha O.
Yeah.
Okay. So now that is one set of probability distributions for O. I want to build my set of probability distributions out of taking linear combinations of these F alphas. And so then there's some weighting I have to do with these functions.
Linear combinations of F alphas. I am not convinced that is a useful way to think.
Isn't that formula? P alpha is sum over O, P alpha.
So P0 is the weight for every A.
But I want to do it the other way around. I want to get PO
From the F alpha also.
from the F alphas.
Yeah. I don't know if you can, that's the right way to think about it in some sense. I'm not sure. Because there's you should just think of it as there's two independent things happening, which is the original state and the coarse graining. And then together that gives you a probability of primary comma bin.
Well, you have a probability of alpha, right? Some
F
some
alpha
number
4.
associated with alpha.
F alpha 4.
4 is that and then you have a P alpha, a probability of alpha.
Yeah.
I was
This is state dependent. This is state dependent.
Exactly. I was thinking that the way of getting POs. Can I write if you don't mind? So P is some function of H. Given every H, you have a probability. F alpha, I'm going to put the thing down here, is also a function of H.
Yeah.
Okay? And so I should be able to write PH as some zeta alpha d alpha. Right? Because this is some basis in the space of all probability distributions of H.
I am not convinced it's a basis.
Okay. I was wondering whether this zeta alpha was this P alpha or something like that.
I don't think so, no. And in fact, I do not at any point require that every probability distribution is a span of the F alphas. I think there might be probability distributions that are just not in the span of F alphas in sometimes.
If you were thinking of binning, that's what I would imagine this to be. choose a set of probabilities for your O's. Like Abhijit was saying, the original probability the original thing was sum over PO was a sum over delta functions.
Yeah.
Sum over the various H's.
Yeah.
That's the probability distribution with delta function here, delta function here, delta
Yeah.
function. Now, bin I would think of as a smeared probability distribution. That is some probability distribution which was smeared around some point. And then just call that a bin, I would imagine you want to do something like that.
I don't want to do this.
That is the coarse grain, right? The coarse
But
grain is the statement P alpha equals sum over O, P alpha come out, right?
yeah, but that's different from this statement.
Yeah, I wanted to write that statement.
Yeah, I don't know where to make this statement.
Okay.
But I'm just saying that like the way I'm thinking of a bin is that you give me a fine-grained variable, I'll put it in a bin. Okay. So
Okay, and can you say that a little more specifically? Give me a fine-grained variable. I give you a PO.
you give me a single O. You like there's a probability distribution. You draw an O. You give it to me. Okay. So for me the binning is independent of the state. Okay. So you just give me an O. I will put it in some bin alpha. Okay. And the point is that I could choose non-overlapping bins so that this is a deterministic function. Okay. But that somehow I care about the case where alpha is continuous. So I want to let the bins overlap so that there can be many more bins than there are fine-grained numbers. Okay. So then I say, okay, I will put, you give me an O, I will put it in some bin, but I will choose the bin via some probability, according to some probability distribution.
This is the point I'm not. What do you give me a O? I'll put it in a bin. What I've given you is a set of POs.
No.
So
What?
alpha is a continuous variable or spectrum valued variable?
It will be continuous in some parts and discrete in other parts. But in particular in the black holes, in the black hole spectra, in the black hole part of the spectrum, it's going to be continuous. So it will be like the area, which is a continuous variable.
Translate, sorry, Shiraz's point for my benefit. I think what Shiraz you're saying is there should be a way. If I gave you the probability for an operator to appear in different bins and sum that in some way, I should get the total probability for the operator for that primary to appear.
Yeah, that is just this equation.
No, but he's saying that's what you're saying, right?
Yeah, I'm saying there's one probability that he's defined a probability distribution function labeled by alpha.
Yeah.
That gives, if it was very peaked, if it was a delta function, it would be the original thing.
Yeah.
So I've got another probability distribution function, one where you're not saying exactly which operator you're on.
Yeah.
Okay. Now your original probability, seems like a natural question to me to write your original probability, your POs, in terms of this. There's a coefficient function there, which sounds interesting. Now maybe there's a measure or something.
I don't know. I don't know where to write it like this. I don't.
Actually, you can get that equation if you use the earlier equation.
Which?
Yeah.
Can you show me?
If this is also P of alpha, F O given alpha, right?
Yeah, sure.
Okay.
Yeah, you can.
Now
Yeah.
you sum over both sides over alpha.
Mm-hmm.
This will be your P of
Oh.
O.
Yeah.
But how do you get
Yeah,
this?
this is same as this, right?
Yeah. I mean,
In a way.
sure, but this is not a useful. This is I'm coarse graining. This is fine graining. That's fine.
Is this statement true with that P zeta alpha equals P alpha?
Yeah, I mean, this statement that he just said is completely true. You can define P of O given alpha. I would write it as well.
P of O is the same as your original.
Yeah, so P O is P O.
But it is what something that exists. Or not.
Yeah. No, you can find it given you have the joint probability. You can always find the conditional probability. That is fine, and you can write P O as P alpha, P O given alpha.
P O given alpha is F alpha.
No, it's a different one. It's a different function. You're thinking of a fine graining process where I give you a bin and then you choose one of the original guys first. This is a fine graining process. But I'm thinking of it.
Probability, right?
Yeah, it's other. That's what. So it's a fine graining. This is a coarse graining.
Okay.
Yeah. Okay.
You use base theorem here, you just get triviality.
Yeah, it's exactly. You define PO given alpha using base theorem.
But
Yeah.
what did you want to do with this?
Yeah, I would have then just substituted that to that and got some answer.
Yeah. You
And just
Sure, you can, but I
Well,
probably
I would then have understood what is P alpha over. That
P alpha
in
is-
this basis of probabilities, P alpha is the coefficient for your state.
no, but P alpha is the probability of finding the bin alpha.
What does that statement mean?
Okay.
Probability for finding the bin alpha, say operational.
Okay, operationally the state has some probability for each microstate,
Each
for each primary. Okay. Now there is some stochastic process which takes each O and assigns it an alpha. Okay, so you draw many O's from your original probability distribution. Okay, and there's some stochastic process which puts an extra label alpha on each O.
O, if you have an O, there's some probability that it's in bin alpha.
Yeah, which is F alpha of O.
But this is some abstract thing, whatever. This bin is an abstract thing.
Yeah, it's a coarse graining.
Okay, fine.
It's what? Like everything, what is not abstract here? I'm confused. Everything is the same level of abstraction here.
It's okay, but it's coarse graining in the sense that the delta function is replaced by something smooth, or what exactly did you write?
Like it's coarse graining in the sense that now each your P alphas really measure the probability that your primary is somewhere around alpha.
What is probability? I mean, where is probability? There was no probability here.
There's a probability here, right here.
Right, there's a probability there, but then that's given. There's no probability of something else.
You can think of
There is a
state,
F alpha.
right?
Yeah, that's a state. Exactly, that's a state.
Yeah, but I'm saying I'm just taking the probability part of the state. Okay, I don't care about psios right now. Okay, so for me the
But
state.
even the full thing can be thought of as some state.
Yeah, it is some state. I'm saying I'm taking the probability part out and I'm thinking of it first as a classical probability. I'll think about the psios later. Okay, for me the state is probability. Okay, and then the coarse graining is something that is not the state is doing, that I am doing to the state. Okay, my measurements are. It's like my apparatus is messy. It can't exactly resolve an O. Okay, it can resolve like if you take a particular microstate, put in my apparatus, it's likely to give some number close to O, but not exactly
That number you are calling alpha.
that number called alpha. And I'm kind of modeling the apparatus by a function which.
So it's not rewriting the state in some other basis.
No, it's not. It's not. It's an explicit coarse graining. It will in fact be a non-isometric map. Okay. That's where I'm going to get to. This is not going to be an isometric map. So it's not just a basis change.
Okay, some probability of error in measurement.
Yeah.
Okay.
Yeah. Ah.
Yeah, so the equation that you wrote, this h of O
Mhm.
is this.
Mhm.
You can write it in symmetric way, right? H of you can take the one on the minus, which is
Yeah, you can. Yeah. But the point is h of O is already in the entropy, so I just want to calculate the original entropy. That's why I wrote it in a slightly antisymmetric way. But you're right, of course. You take this guy on that side, it's exactly symmetric. Yeah. Agreed.
So now this is coarse graining, like you go from a definite state of a gas to some pressure and that.
It's some sort of thing something like that. Yeah.
Ignorance.
Yeah, exactly. It's coarse graining.
Okay, alpha is like the EDM energy.
Yeah, it's.
Always there with fine grained CFD.
Yeah, exactly. That's exactly right. Yeah. The point is that even if after my apparatus measures a specific value of energy, which is alpha, there's actually going to be a non-zero entropy left in the state because of this uncertainty.
So that's what your area is going to be.
That's what my area is going to be.
And what about the choice of F alpha?
That's a great question, and I will comment on this later.
Yeah.
There is a particular order one ambiguity that will stay, and then the question is it there in gravity or not? That's a concrete check of this story.
So what was the question? Choice of F.
I'll get there. Yeah, I'll get there. Okay. So now let's just yeah.
About the F alphas, I'm thinking of it as some kind of Gaussian spread. Does the size of the spread stay the same throughout? Like you just pick one size and you just shift the positions?
If you F alpha. Oh no, it's a set of functions. Like whatever my apparatus's resolution might depend on the actual value of the energy, right? Like that is allowed. I won't need it to have a specific behavior beyond something that I will impose later.
Okay, thanks.
Yeah.
So here,
Huh?
change I could hear clearly.
Okay. Right. Huh.
So here, if even if your CFT had degenerates, this is where it would stop mattering, right? Because
Yeah, completely stop
when you
mattering.
are
Yeah.
mad,
Yeah.
then you are.
Exactly. Yeah. Cool. So now let's just evaluate these various terms. So I will assume, for simplicity, that PO is slowly varying within a bin. Okay. That the probability is not very fast varying, that your apparatus is not completely useless for the state of interest. So I will define PO to be P alpha. Oh God, I will just look up the exact formula.
So you want to expect lots and lots of states to be in a bin, or
I will want lots and lots of states. Lots of states to be in a bin. Yeah. In fact, I will argue. What we'll find in CFT is that if you choose the bins to have order 1 width, there will be exponentially many states, because that's just what CFTs are like. Holographic CFTs are like. Okay. So you take PO to be like an average plus a variation. Okay, where the variation is smaller than the average in some obvious way. Okay, and when what you find is that HO given alpha, okay, is dominated by this n alpha here. Okay, so you get
what is n alpha?
n alpha is the number of states in the bin. Okay, so you get integral of d mu alpha p alpha log n alpha. Okay, plus order of delta p alpha o square. Okay, so it's quadratic in the in the error. Okay, and h alpha of o given o is just going to be minus sum over o p o integral d mu alpha f alpha log f alpha of o. Okay, so look at this very cute equation. This is like a continuous entropy. Okay, it's an entropy of the probability distribution f alpha of o, and you're just averaging over o. Okay, so this is telling you basically and this is obvious from the meaning of conditional entropy. It is the average amount of uncertainty in alpha once you have a fixed o. Okay, and if this is bigger than the other terms, then you have a very bad coarse graining, because you have too much uncertainty in the bin. Your bins are too big. Okay, and here there is a error due to the fact that the actual probability distribution is not fixed within a bin. Okay, and if this becomes comparable to everything else, that means that your what do you say? That means again that your state is not semi-classical. Okay, so this is like a semi-classicality constraint. Okay, it's going to be. I haven't still introduced any semi-classicalness but yeah, it's going to be semi-classicality, and this guy is basically a constraint on binning or coarse graining or resolution of the measure of the apparatus or whatever. Okay, so these are the two things that need to be spoiled. Oh, yeah.
Is P alpha when, let me take an operator O, it may not lie in some bin, right?
I choose my bin so that for every O, then this bin probability for all O this is 1. So every operator is covered by at least one bin.
Every operator is covered by some bin, but here alpha is fixed to be some number, right?
Where?
In P0 equal to P
PO. Oh yeah, that's right.
So every operator is covered by some bin, but there can be an alpha where the operator, some operator doesn't lie, right?
Right?
I mean, you know, your operator is way out on the right and you've chosen some bin here to the left. So that's possible, right?
Yeah, sure, but the point is that
So
anyway, the contribution of that is going to be separated by the fact that f alpha of 4 is basically 0 on that pair.
FL will be, I mean, therefore writing this formula because
Yeah, this is within a bin, so okay.
it's for operators which lie within the bin.
Yeah, basically, yeah.
That's the point,
Yeah, exactly. Otherwise, you would be like, okay, each O lies in different alphas. So which alpha should I put here? So like for each bin, I'm doing this. Okay, yeah, you should. Sorry, I should have been more careful about that
Given
statement.
an operator lies in a bin,
No, yeah,
then it is basically P alpha,
yeah.
which is all the sum over all operators lying in that bin,
Mhm.
the probability divided by n.
Yeah.
N is what? N is
N is the total number of operators in the bin.
total number of operators.
So the bins are not overlapping, right?
They are overlapping.
Overlapping.
Diagram.
Oh, okay.
This overlappingness is kind of crucial because I want to cosine a discrete set into a continuous set.
Okay.
Yeah. So now, yeah. So this expansion is I'm deploying it within each bin separately. Okay. Yeah. So you have to be, yeah, that should be careful. Yeah. But the point is this constraint on binning is linear in the state. Okay. So let me just write this. This is linear. This semi-classicality constraint is non-linear. It has
Can you explain that semi-classicality constraint again? Sorry.
yeah. So good. It's right now I'm kind of reaching with this word, but basically semi-classicality is a statement that your probabilities of the different microstates should vary slowly. Okay. So that means that the for a given bin, the contribution from the variation within the bin should be suppressed compared to the average. Okay. So this being small is like a semi-classicality constraint. Okay.
It should vary order one in the spectrum.
Yeah, exactly. It's I really should.
E to the minus.
Yeah, I'm slightly doing it in bad order. F alpha 4 will have order 1 width, and this guy will have like basically some order 1 derivatives. Okay, and the fact that it's the same order doesn't matter because of the square. Okay, but yeah, so if it's less than order 1 derivatives, sorry, the derivatives are bigger than order 1, then this guy gets big, and that means that you're not in a semi-classical state anymore. It's like you're more focused than a microcanonical ensemble. Okay.
So what is the case when delta p alpha is 0?
If delta p alpha is 0, then you're in a very, very flat state somehow. That is also a very weird state.
The thermofield double.
Thermofield double, this won't be 0. It will still be G Newton or something. Okay.
I'm still having, to begin with, H 0 slash alpha is that object, right? Integral d mu alpha. Now, what is the, I'm still missing, what is the expectation that if the probability for every operator which lies in the bin is roughly the same,
Then they should be dominant. This is the average of the. This basically, see, what is this? This is basically just telling you that the uncertainty of the operator given alpha is just the log of number of operators within alpha, within that bin.
Okay.
Right?
Yes.
Which is what would happen if you had a flat probability distribution. But then there are corrections because the probability distribution is not flat within the bin, but it's quadratic in that correction. Okay. Yeah. And what I wanted to emphasize was this constraint is not linear. Okay, because it's quadratic in the probability. Okay. This constraint on like my apparatus is a linear constraint. Okay, it's fine. Like, but this is so like you could imagine that you could impose this at the level of a code subspace. This constraint cannot be imposed at the level of a code subspace. It's because it's not a linear constraint. It's not closed under linear superposition. Okay.
Why is it not linear? Sorry.
There's a square.
O square, what does that mean?
It's the square of the square of the delta p. Let me just remove the subscripts to make it clearer. Okay, the square of a probability. It's a quadratic constraint.
Sorry, I missed. Why is there no linear term in the error?
It just works out that way. It's because you have to the usual thing where you take the delta p alpha O sum over, because it's an average, the sum over these guys is 0. Okay, and that makes the linear term go away. This is like you see this all over the place in perturbation theory. This this is also the reason that relative entropy starts at quadratic order. Anyway, so the point is that the coarse graining gives you something here. So now this guy is linear. It has only one copy of the probability. Okay. But then you have these two constraints on this guy being trustworthy. One of them is a nonlinear constraint. Okay. And now, because this is a linear constraint, I can write down an area operator, which is just integral over d mu alpha log n alpha sum over O f alpha of O, the projector onto O. Okay, this is literally the expectation value of that operator. Okay, so this gives you an area operator in the coherent setting. Okay, for states that satisfy some nonlinear constraint. Okay, this is very crucial. That this area operator only lives on a nonlinear set, like not a linearly closed set of states, and this you should have expected because coarse graining is not a linear thing. Okay, coarse graining is like something that's not closed under superpositions.
I'm sorry
Yeah.
to do this, but there's probably some trivial algebra that takes you from the actual definition of 0 alpha to what you write here, right?
Mm-hmm. Yeah. Do you want me to go to the algebra?
Just if you can. So basically, I have p alpha 0, which is the probability to get the bin alpha given 0, and on the right hand side, I have some entropy associated with the fact that on given alpha.
Are we on this line or that line?
Here's the second line.
Here, okay, okay.
Second line, first term should just come by putting into the underlying definition the fact that P0 is P alpha over N alpha with small variations. Right?
Yeah.
I'm not quite able to see that, and I'm sorry.
Okay, no, we can do that. We can go through the math. Yeah, okay. Let me just do it here. I will rewrite the area operator again. Okay, so we have PO equals P alpha, sorry, P alpha O over PO, that's what we wanted, right? No, P alpha is equal to, sorry, this should be P alpha O. I'm sorry.
Oh, okay. So
that was the mistake.
it's part of my confusion.
Yeah.
Okay.
Yeah. So this is 1 by N alpha plus delta P by P alpha. Okay, and then the 1 by N alpha inside the log just gives you this piece. Okay, and then basically you expand the log. You use the fact that sum over O of delta P is 0. So then you just get the quadratic piece as the first correction.
Now it makes much more sense.
Yeah, thank you. No, you're right. This was a important mistake I made.
Okay. So now I have a better chance. Okay.
Okay, yeah.
So Ronak, in what sense the third term is the code subspace entanglement?
This term?
That's the area, right?
That's the area.
But then there is I thought there is a code subspace entanglement.
That is this part, which I have not which I have kind of skipped. Okay, that is the.
But on the right hand side of Harlow's theorem, there was only the area and that, right?
There's area, code surface entanglement, and Shannon entropy over the alpha sectors, which is this H alpha here.
That's that H alpha. Then that's the area. But then what is this additional stuff here?
These are corrections.
No. Both of these are
Yeah, these are corrections. These corrections have to be small, and them being small is two different constraints. Okay, this is a constraint on my binning procedure, which is a linear constraint, and there is a constraint on the state being sufficiently semi-classical, which is a non-linear constraint. Yeah.
Sorry. In the blue box thing, is it P alpha 0?
It's P alpha is the total probability of the bin.
Acha, because you sum over the zeros then.
Yeah.
Yes.
Yeah.
At least
Yeah.
okay, yes, okay.
Yeah.
Sorry, sir, I got lost in all of this. But the key point here was that this thing was linear in your state. Right?
Yes, this is linear in the state.
So it was not linear as an exact thing, but it became linear because of some approximation.
Yes.
And can you just
The approximation is the fact that the probability is slowly varying within the bin.
yeah, no, can you just show where that nonlinearity, where was the nonlinearity and how it went away?
So the nonlinearity here was just the fact that it like everything here depends on the state, and there's a log and like.
And what did you replace to make that go away?
So the point is that I said that this ratio here is approximately constant.
Was it independent of O?
Yeah, approximately independent of O. Okay, it just gives it's just basically the number of things in that bin, which is 1 over n alpha here. Okay, and that gives you a linear part.
And again, why was that the case?
Because basically, I'm just saying that because it's slowly very.
Flat.
Yeah, it's flat, and so like the entropy of a flat distribution is always just the size of the space, log size of the space. Yeah.
But I don't see why this term is small.
This term?
Yeah.
It's not obviously small, and I will. I should get to CFT now.
Looks like order 1, right? Depending just
It,
a matter of f of alpha.
Yeah,
It's an order 1 function.
it's going to be it's an order 1 function. Yes. Yeah, that's true.
Okay.
But it's smaller than the entropy, which is order C.
Okay.
Yeah, and it's smaller than the universal correction, which is log C. So microcanonical entropies have a universal log C piece, and this is going to be smaller than that. Okay. Yeah. Good. So just to say what just happened, we get h of O is equal to the I'm going to write this as sum over, let me get this right, integral d mu alpha log n alpha sum over O f alpha of O probability projector on O plus the Shannon entropy over the alphas, okay, which are the cosine variable, plus corrections, plus again you can do a similar analysis here. Okay, you demand that the quantum state is slowly varying in O again, and then you get integral d mu alpha p alpha s of rho alpha plus again corrections, which again have a nonlinear and a linear piece. Okay.
Sorry, and maybe this, sorry, what somebody passed right at the beginning, but that P alpha O divided by P alpha is like 1 over n,
Yeah.
but for some range of O's.
Yeah, because yeah.
So isn't that dependence on that, depending on O, isn't that a secret dependence of O?
No, because it's that range is given by the f alpha of O. It's like it's given by the binning. It's not dependent on the state.
Oh, I see. Okay.
The binning is state independent.
But in this formula, alpha was supposed to be this code subspace alpha, right?
Yeah. So now.
Particularly it was diagonal, the code subspace in alpha.
Yeah. And this is also diagonal. This is also a diagonal thing, roughly. Okay. It's close to just being like sum over log n alpha p alpha, but it's just there's some small corrections. Okay. And yeah, the point here is that this is exactly Harlow's form of the entropy, where this is the area.
What did you do there? So you
Yeah.
have the top H0 there, and
So I kind of put everything together. Okay, so this term, the blue box is this term. Okay, because that is linear in the state. I can just like do this. This guy gives you p alpha, and this is log n alpha. Okay,
okay,
and yeah, this is sum over O.
okay, that's that.
And then h alpha is here.
Is there? Yes.
Here, and then this term I will put this term through a similar ringer, and I get a leading piece which is this, plus again some corrections, which will also be like some linear piece, non-linear piece, and has some similar interpretations, which I just don't want to get into right now. But because this is the main point. This is just a repetition.
So P alpha given O, as you said, was some kinematical data, independent of state.
P alpha given O is kinematical. That's right.
So then there's only one appearance of the state in that sum, namely P alpha.
Here?
The second term up there.
Here? Not completely, because this is not exactly a fixed ratio. There are these correction terms.
Right. No, but of those three terms, P alpha given O, P alpha given O, and P alpha, only P alpha depends on the state.
No, P. This is a joint probability. This is not a given probability. This is not a conditional probability. This is P O times F alpha. Yeah.
I see. But, so the two occurrences of the state are in P alpha and that P alpha.
Oh, yeah. So the point is that the state dependence of this ratio is approximately cancelled out.
I see.
Okay. Yeah. Yeah.
Just the second line on the left, SE psi L, what exactly was it?
It is the entanglement entropy of the state psi reduced to the left boundary. Reduced to the.
You take the density matrix of the left boundary and compute.
Yeah. Yeah. Cool.
So the left hand side should be SC psi right there.
Yes. Thank you.
All those P alpha comma O's are joint probabilities?
Yeah, these are all, everything here is joint probability. Where there's no lines. The lines make it conditional.
Lines make it conditional.
Yeah. So yeah. Sorry, maybe I should have explained that notation.
Okay.
Yeah, but yeah. So commas are joints.
Sorry, what was the reason the area term being non-linear?
This area term is linear. The point is I extracted a linear piece out of a H of O. This is non-linear, but basically because it has some structure in it, this probability distribution, I was able to extract a linear piece, okay, as the dominant term, assuming that some correction terms are small. Okay.
But you said some time that area, this coarse graining induces some sort of non-linearity.
Yeah, that's what I'm saying. So like the what is it? The area term appears with when this constraint, when these two terms are small, but this term being small, this term is quadratic in the probability, right? So it's non-linear in the state. The constraint on the area term emerging is a non-linear constraint. Yeah.
And somehow the non-linearity went away up to small corrections, let's say, because if an operator appears in a bin, its probability to appear in the bin is independent of which operator you're talking.
Basically, yeah.
Somehow that,
Yeah, there's an approximate flatness within a bin.
that's the key.
That's the key point. Yes. That this is the reason coarse graining ever works. You know, because you have a bin and like it, what do you say? It doesn't much matter where you are in the bin. If this did not happen, then coarse graining like would not work.
So this is some familiar thing that other situations also where this entropy becomes expectation value of some operator.
Yeah. This is a for ds equals dq over t, where you integrate that up is s like the differences in entropies are just the amount of energy you throw in over the temperature. And this is a linear thing. This is an observable. It's generic in thermodynamics is my point.
See, in the Harlow's case, the code subspace had this structure of direct product, direct sum over alpha, right?
Right. Here it
Where
is
each
not.
term is a
Yeah.
direct, product.
Yeah.
Here there is no.
Yeah. Here there is a similar structure with the O's.
Oh, yeah.
Okay. but it kind of is not it is not the thing that gives you area. Okay, the area is not irreducible within each, like there is an exact direct sum structure, but there is no it is irreducible entropy within that exact direct sum. Okay, but there is an approximate direct sum, which is where there is irreducible entropy, which is the number of primaries in each bin.
But what if I kind of use the following? I mean, so there is some sort of entangled state, and then the code subspace is where you just act with the stress tensors, which is what you had actually, the stress tensors to make descendants. And this action can be entangled.
It can be entangled. That entanglement will go in here.
Yeah, but then you kind of have a rough direct product structure, right? Because there is this direction of primaries and this direction.
Yeah, it's true that in an ICFT, the Hilbert space looks like the identity module plus H primary tensor H descendant. Okay, because it's irrational, and there are no in a generic ICFT. There could be some weird accidental null states, but yeah, that is true. But that is somehow not the right picture for area, for geometric area, because the descendants are boundary gravitons. They should not encode any area term.
No, not descendants. I'm not talking about descendants encoding the area. In fact, the primaries would encode the area, and the descendants.
That is exactly what I'm going to say.
But here, the way I said it, it didn't seem to require any alpha business and coarse graining.
Because well, if you had some guarantee that you only get primaries in bunches, okay, if you write down a code subspace where you get primaries only in bunches, then the entropy over primaries would give you an area. But at least my code now, and I agree this is a very blunt sort of stupid code, did not give the guarantee that primaries come in bunches. My code allowed for singing.
Primary comes in bunches only, then it's true. What does that mean?
Let me maybe get to CFT and maybe that will become clearer.
Let me ask you a remedial question. I mean, I thought the crucial thing for Harlow was that there was a direct product as came up earlier.
There was a
there was, so you of course have complicated things for me by having B bar, but let's take B.
Yeah,
we had B1 and B2, right? There was a tensor product there.
Yeah.
You were encoding things in B1 and B1 bar, but the other guy, the tensor product, was encoding the area entanglement.
I agree.
You don't have that tensor product.
I think it's approximately emerging, and it's right now. See, right now this entire board, there is no quantum mechanics.
There is no quantum mechanics.
Right. So, but the evidence I give you for it, there being an approximate tensor factor is this term here. Okay. It kind of looks like you have like some state with log n alpha entanglement. Okay, different sectors. In each sector, there's log n alpha entanglement that you're not touching, and this kind of gives you the probability of that sector. It's an approximate feature, but yes, I have not put in quantum mechanics. This is why you don't see the tensor factor.
Also, there is some sort of tensor factor, right? Because you can have, let's say, the Hilbert space of just primaries and the Hilbert space of a Verma module. And if you take a direct product of that, you would have primary.
No, the point is that H primary, the Hilbert space of just primaries is
there is no null states.
Yeah, the Hilbert space of just primaries is what is popping out as an approximate tensor factor, which is what this is measuring.
Yeah, that's what I'm saying. But the way I said it, can I not just utilize this particular direct product structure
but I did
without using any alpha? And
but that's what my original thing was, no?
Code subspace entangle the entanglement, encode the entanglement, code subspace just have the entanglement of the Verma module part.
But this is exactly what this is. I am using H prime.
Alpha. How can I say it without alpha?
No, I'm saying that here there is H prime. I'm just using H primary tensor H descendant, and I'm kind of tensor factoring off the primary and descendant parts. And this is just a general state in the tensor product Hilbert space. Okay, but that did not give you an area term, is what I'm saying.
How can that not give the area term? Because there is a tensor factor.
Maybe
there is a primary level entanglement which should be captured by the area. Right?
Here the primary level entanglement is captured in the Shannon entropy. The point is not a linear piece.
Oh, I see. Because but let's say let me mention, write down Harlow's theorem without any alpha. Can I do that? I can do that, right?
But then the area is a number, not an operator. Yeah, I care about the operator.
Okay.
And I see.
Yeah. But at least in that context,
Yeah.
where area is a number, let's say, not an operator.
Mhm.
In that context, you could use just the. In other words, what you are saying is that it is not just the direct product structure, but it's sums of direct product structure. And the way I said it, it just had a direct product structure
Yeah.
with one term.
Yeah, that's not.
And
That's
when you get
no,
multiple terms like that,
no,
then
no,
you
no.
use
That's
the
not exactly
some,
right. That's not
some
exactly.
label as being area.
That's not exactly right. Let's get back to this after I make it concrete in CFT.
Okay.
Yeah, this is like yeah, because I want to get to CFT right now. Yeah.
Sorry, okay, so when you talked about the sky, you said these are some high energy degrees of freedom.
Yeah.
So in this particular example, are you
The chi's are going to be like it's going to be like a maximally entangled state within this bin, and the idea is that it's not high energy, but you need a lot of resolution. You need a lot of resolution to actually differentiate these different states. Okay, so you can kind of think of these as like yeah. The point is that the spacing is not you can't resolve it without exponentially many measurements. It's more complexity protected than energy protected here.
I thought in the energy of the primary spectrum, you would put a cutoff at some.
I am not going to do that. I am allowing arbitrarily many primaries, arbitrarily heavy primaries. It's okay.
So yesterday there was no.
And even if I did, it won't change any of this story. I could say, oh, my primary is like bounded by some polynomial of C. Everything I'm saying is going to be linear in C, so it doesn't matter. Huh.
There was no constraint on area term yesterday on that chi alpha, but now here you can.
Because this is concrete, that was abstract. That was just a statement about any quantum error correcting code satisfying some conditions. This is a particular, there's a particular physical Hilbert space which is 2 CFTs and a particular code. So now there are obviously more constraints here because it's a concrete thing.
What happened to the factorized state?
Which factorized?
This code also has factorized state.
It will fail the nonlinear constraint.
The delta.
Yeah, basically like it's going to, because the variation within a bin is going to be equal to the average.
So you're just discarding. So now you are basically. Can I think of this as a criterion for discarding factorized states?
Yes, and it's a nonlinear criterion. Yes, that's yeah, exactly right. Semi-classicality is not a linear criterion. And that's kind of what this is kind of why I chose a stupid code subspace. I thought this is a good thing to stick with.
And then once you have this formula, you still, at least I assume, approximately have all the other good things like.
Yeah, exactly. This is like approximate error correction.
Yeah.
It's like an Harlow theorem for approximate error correction.
Right, because of all of the above equivalent states.
Yeah, I have not proved the TFAE, but I'm sure it can be proven. I'm not tried it yet.
I didn't understand that. If you had a tensor product.
Oh, you could do this approximate decoupling or something?
Yeah,
Yeah.
This
Yeah,
is
that's
approximate
actually.
decoupling and that of
Oh,
course is
that's nice. That's nice. That's a good idea. Thanks. Yeah, we should talk about it.
Sure.
What are you saying?
No, I didn't quite see if you had that tensor product state, why is it going to be one where the variations are big?
Oh, simply because you have a bin. Okay, where's the blue chalk?
I don't understand the question.
So like the bin is like this, okay, and the probability is like this. The probability distribution is like this. Okay, it's like a single delta function, and the bin is like this. Okay, so you can see that the average is clearly as big as the fluctuation because at various places it just goes to 0.
But, okay, and the criteria was that the probability, if an operator is appearing, then its probability should be regardless of which operator. I see. So you're saying, suppose the state was the tensor product, only one operator is appearing.
Yeah, and so it's like
So
a.
it's just that there aren't too many operators appearing.
Total distribution should be smooth on size of the bin,
Yeah,
and that's not true.
exactly.
So that second thing going to that thing is totally wrong.
Exactly. Yeah, you can't do the expansion in delta p alpha. It like makes no sense.
So you're going to get a minimum sort of kind of entropy, which is going to be size of bin, right?
Yeah, that's exactly the entropy. That's exactly the area operator. Cool. So now let's cut off the discussion and like go to CFT. Okay. So
It's a quite different structure mathematically, right? From
it's a very different structure, and that's why I find it cool. Like if I had just done see, this code structure by the way has no bulk local degrees of freedom. If I hadn't done this coarse graining, I would not be talking about it, because it's just like it's the most obvious thing you can do.
Boundary graph.
No bulk degrees of freedom. You have boundary degrees of freedom. Just yeah, it's not interesting. Like there's no Susskind-Uglum here, right? Like what's the point of doing Harlow in real AD CFT if you're not doing Susskind-Uglum? If we can't do Susskind-Uglum, like you have to see Susskind-Uglum, otherwise it's not useful. Okay, so let me just keep that formula here. So holographic CFT, I was using this color, right? Holographic CFT, hol means holographic, has the following property that for, again I'm going to assume that like there is no spin in the CFT, but that's just for notational convenience, nothing important is changing.
The Hilbert space is such that you cannot change all these things, because the only operators you allowed were stress tensors, I mean your operations.
Yeah.
So all of this is like once and more for all fixed entropy.
Yeah, you have to import PO and SIO.
And it never changes through your life of putting stress tensors.
Yeah.
Okay.
That's right. What changes is that if I do something non-semi-classical, these corrections become big.
Right. No, but once you start your system, then you put as many stress tensors as you want. Nothing here changes, right?
If you put exponentially many things, everything will change.
The descendant part. Yeah. Right. Not counting everything we talked about here.
Like your
Yeah.
Only concept about
Only
the
the
primaries and the probability.
So this is like frozen forever in your space.
that's like the bulk degrees of freedom not by changing the black hole horizon.
Yeah.
Yeah. Well, we can discuss this a bit in
But
this.
as Ronak is saying, you can start violating these semi-classical.
Yeah, you can make it like less and less semi-classical actually.
You can, but even that, however, whatever you do, that's frozen forever. In your
What do you mean?
space.
Frozen in
Choose the state, right? You make it.
You can choose the state, but you cannot change that state by putting stress tensor. So in this set of allowed operations, you're not changing anything.
What are you? I am the
I mean,
opposite.
the state in a sense is defined by the probability for the primary.
Right.
So that's
Fixed forever.
That's
See, this operator, which is a purely Lorentzian operator, projects you onto a factorized state.
Projects you onto a.
Just evolve it.
No, but in time evolution, in Lorentzian time evolution won't change. You've got some state tensor.
Hidashiras.
Huh?
I.
But
It's Lorentzian time
I
evolution.
without that integral dt, it just gives you phases.
Oh, okay, yeah, sure. You're sticking to Loga would get angry at you for ignoring.
No, I mean, you make your system.
Okay, yeah, right. Yeah. Fine, yeah. Without any other, if you're allowing only forward time evolution, then yeah, you're right. Cool. So the holographic CFT, I'm again ignoring the possibility of spin. If so, you have only a.
With stress tensor. Oh, with stress tensor.
Yeah,
Huh.
projection, not unitary.
Yeah. Delta greater than C over 6.
This horizon area changes with time.
Horizon area, what?
You throw stuff in. Oh, you mean that the horizon at the bifurcation.
The bifurcation it will not change.
And also, there's no bulk degrees of freedom here. If I could throw stuff in, then I would have to worry about Susskind-Uglum, which I am not worried about. Yeah.
But effectively, I mean, the entropy of the entangled stuff changes, right? You can make a bigger black hole.
I mean, the coarse grain.
Yeah.
Okay. But that's a different coarse graining. Okay. Which I don't know the relationship to this coarse graining. Okay. Cool. This anyway. So then holographic CFT. There's basically 3 ranges of the dimension. For delta less than C over 12, you have a sparse spectrum. Okay. So you have the number of primaries below this does not scale with C. Okay. and you want your alphas to basically, your bins to basically be like the delta functions, okay, just like a discrete set, which one at every microstate. So alpha discrete, alpha in primary spectrum. Okay, here in this range, and this is not universal, and what you want to do depends on your precise CFT, and I will not say more. Okay, and here what happens is that if you consider the number of primaries in an order 1 window, and someone last time mentioned Tauberian theorem. This the following statement is derived by Tauberian theorem. It is equal to roughly speaking c to the minus half order 1 corrections times c to the minus half times e to the square root c minus 1 times the delta of the primary times some number, which is the same number you find in the Cardy formula. The difference in the Cardy formula is this minus 1 and this c to the minus half.
The minus 1 is because primary is not descendants, right?
Yeah, primary, it's only primaries. Yeah, and it's the same with the c to the minus half, I think. Okay. Another fun fact is that this is the modular crossing kernel of this is equal to the modular crossing kernel of Liouville theory up to some order 1 corrections. Okay, and this is because this is actually a general factor about Virasoro representation theory. Yeah, well, delta is like q squared by 4 plus p squared or something. Yeah. Anyway, this is just an aside. I mentioned this aside because log of this kernel was the log of this kernel was identified as area by Mertens, Simon, Wong. 19, no 22. Yeah. So that this is equal to e to the area. Okay. So and basically this guy is the log n alpha here. If I take f alpha of O, and I'll focus on now. First thing, by the way, this area operator knows about the Hawking phase transition. Okay, which is a nice thing. Not super non-trivial, but it's cute. But let's go above the Hawking phase transition. Who cares about thermal radius?
Because the number of states.
Yeah, yeah, cool. And this f alpha of O, take it to have order 1 width in O space. Okay, and then therefore you can apply this formula with some order 1 corrections that depend on the actual shape of f alpha of O. So this is some ambiguity. Okay, and so you get that your log n alpha is log S1p alpha. It's an unfortunate clash of notation that Liouville theory has is completely different alpha, but this is our alpha, not Liouville's alpha, plus order 1 stuff. Okay. So basically this is the concrete thing, and you can see that the area comes from the uncertainty, like the fact that primaries come bunched together in these many in groups of these many. Okay. It does not come, the H primary itself gets its approximate tensor factor tensor decomposition. Oh.
I think I'm missing something. So you might have said, you probably said this, first term is supposed to be the area term, is that right?
That's the area term, it's linear in the state.
It's linear in the state, and is there a further reason to think it's the area term?
So good, basically you can, it's the basic argument is that this is the part of the entropy, okay, which is not this is not coming from the boundary gravitons. Okay. Because the boundary graviton entropy is
P0 on the probabilities for the primaries.
Yeah.
Is that the point?
Yeah, exactly.
And your course grading.
Yeah. So in general, like this is the part that should equal the geometric area, because this stuff is all boundary graviton stuff, which is at the boundary. Okay, and because there's no bulk locality, everything should be at the either at the boundary or at the horizon, and this is dominated by this piece. Okay, for sufficiently good states, for states that are microcanonical ensembles or wider.
Yeah, from the area term, can we see that only those primaries whose delta is greater than c by 6 will contribute to the area term?
Yeah, basically because this log n alpha, okay, for alpha less than c over 12, yeah, for alpha less than c over 6 will just become 0, because that's just the number of primaries within a bin. You make a bin however you want, okay, order 1 bit bin for log of 1 is 0, yes. Yeah.
And in this formula, just to get some intuition, if this that a row of O was the density matrix of O, so if I made that spectrum broader, does that
Rho O, if the spectrum of rho O,
yeah,
this is okay. It's okay to have very quantum boundary gravitons in this story.
sorry, wait, this was the area term I was looking at.
The area term.
Yeah.
So rho O, PO.
Yeah.
Yeah. If you make it very broad, then what happens is that the binning constraint actually breaks down.
No, but I make it broad, but not broad enough so that breaks down. Does that entropy increase?
No, because this is of this log n alpha is a fact about the binning. What happens is that you get contributions from many more bins, so the total entropy does increase, but not log n alphas.
Right. But you make it clumped. I understand that the big factor times a number, and that number becomes bigger as you make it broader.
Yeah. That's right. Cool. What else did I want to say about this? You get, and basically like Mertens, Simon, Wong, and also McGough, Verlinde had kind of identified that this would be the area term based on like Chern-Simons theory and so on. And this is just, and also from the common sense argument that this is the part that's not boundary gravitons. So there's a good reason to believe this is geometric area also. So now let's just look at so this h of alpha given O, which was the binning constraint, it basically becomes log of width of f alpha O at peaked alpha. Okay, this guy just like you look at in the state which alpha has the most probable, and log of width of that f alpha is going to be this correction term. Okay, and because width of these guys is order 1, this is order 1. Okay, so that is fine. And similarly, if you take a microcanonical state, you can argue that because the other correction, the semi-classicality correction, is quadratic in the width, you also find that is small for good semi-classical states.
Can I ask you something about the area being identified like this? Except for some very small correction, it's the entropy of the black hole, right?
That's true. That's
So, I mean, without being anything fancy, if I'm working to leading order and yes, this is the area.
I agree.
I'm just saying.
I agree. This is the microcanonical entropy. That's right. This is minus half is like. Yeah, exactly. I agree. Okay. This is the final result. Again, I am emphasizing that the final result. Yeah. Yeah, exactly. It's the entropy of the black hole, and the Chern-Simons kind of also gives you the -1 and so on. Okay, so you have to a little more, but it's fine. The point is Chern-Simons kind of works where the boundary theory is like whatever Liouville, or more precisely Alexei Shatashvili with identified 0 modes or whatever, which is not a holographic CFT. The point here is that I derived it from a holographic CFT, and the other point was that this only works for semi-classical states which satisfy a nonlinear constraint. Okay.
And sorry, where is PO information going? It's just
Here?
Order 1 correction.
It's the expectation value of this projector.
And so if I change my state, it's like getting black holes of different areas.
Yeah. Like yeah, basically every good state has like some width in the black hole area, or at least order 1, usually at most order 1 by root g Newton, and typically yeah that would go into this.
Yeah, so but a semi-classical state has more or less one area,
Yeah,
and then you get that.
yeah, yeah.
So again, you're saying if you change p zeros, that's like changing.
It's sort of like the over what energies
Yeah,
are
yeah.
supported.
Yeah, exactly. It's exactly that.
Yeah.
Except the except it's the the primary energy, not the full energy.
Yeah, yeah. So different energies have different associated areas.
Yeah.
The kind of things that you're calculating, why should this depend on the type of binning you choose?
It does, and what I'm saying is that these are order 1 corrections. So there are order 1 corrections here depending on the bin. There are order 1 corrections here depending on the bin, and also the HO given alpha will also give order 1 corrections that depend on the bin. Okay, so the point is that I can only trust this formula up to order log C, not up to order 1. Okay.
But let's say I'm calculating, let's say entropy. Right? Why should it depend on what type of like function you are choosing? It should be just something, right?
That's a question to like. Is there some place for the order 1 corrections to go in the gravitational calculation? Where see at leading order the order 1 corrections are not there. Okay, so when the things we usually do, we will not see any of these issues, because leading order. Honestly, black hole entropy is such a weird thing that you can do all sorts of nonsense and get the right answer at leading order. Okay, but to keep track of the order 1 corrections, you have to do careful one loop calculations. Okay, or maybe even beyond one loop. I don't know.
Yeah, but it should be some answer.
It should be some answer, and that's right. And question is, are there any ambiguities in gravity for these order 1 corrections to go, or does gravity pick out a specific binning function, or am I just wrong? There are three possibilities. The only way to distinguish them is to do the calculation, which I have not got to yet.
So let me just summarize what I'm
Yeah.
You've got the spectrum, this Cardy spectrum on one side, you've got a Cardy spectrum on the other, and you restrict your attention to states that are entangled over energies scales large compared to 1.
Yeah.
Okay, and therefore the entanglement entropy is the Cardy.
Yeah.
Is the Cardy.
Yeah.
Why is that surprising? I mean,
The answer is not. The answer is deeply unsurprising.
Okay.
I'm saying the important thing is that to get this structure.
The linear operator was what was interesting.
Yeah, getting the linear operator on a non-linear set of states is what is interesting.
Yeah, I get it.
Yeah, the answer is stupid.
Yeah.
Okay.
Is there some sense in which the nonlinear constraints that you got for the state to be semi-classical can be interpreted as this linear area operator as being semi-classical, like its fluctuations being small or something like that?
That's a great question. Probably yes.
Say again, what was the question? Sorry.
I was just wondering whether there are these nonlinear constraints now, right, which identifies for you the orbit of semi-classical states. And you could have wondered whether the same constraints can be picked out by saying that my area operator is classical. Right?
Yeah.
Of the area operator are small.
That's a great question. I don't know. Yeah, I think it should be possible, but I would have to think about how to do it.
Usually in gravity we think of semi-classical states as those where either the area operator has small fluctuations or some geometric operator has.
Yeah. The thing is, that's what we kind of just go with our guts and write down linear constraints. I was just this kind of gave me a nonlinear constraint for free, which seems more sensible for a semi-classical set. Yeah. Now, of course, it should be also almost equivalent to making the fluctuations in linear in some like a squared minus expectation a squared to small or something. But it would be interesting to understand the difference.
It may not exactly be the area operator, but
Something like this. Yeah. Like it be. I don't have a good account of what the difference between the nonlinear constraint and any obvious linear constraint you might write down is.
The nonlinear constraint was that the distribution was slowly varying on this.
Yeah. Exactly.
So Ronak, can I try to understand it in the way that Harlow's theorem was understood? So let's say here alpha was a continuous variable. But I can think in terms of, let's say, for now for moment discrete binning. So you have order 1 bin, then next, and then next, and so on. Now, to begin with, as we discussed, the structure of this is primary tensor descendants. But now if you have this binning structure,
Yeah,
then what you can do is bin can number your alpha.
Yeah, that's right.
And then you have inside there is an extra direction which is the primary, and then there is a descendant. So you can get alpha h prime primary times h descendant, and that is the thing that is being described in some sense here.
Yeah, exactly. So this is approximately h alpha tensor h bin.
H alpha what? No, h primary. This you're writing this.
No, I'm saying the
No,
the
I'm
total
writing-
thing. The total thing.
No, not total.
This is the h of the various alphas. This is like an L2 of R.
No, I'm thinking that each bin has a tensor product structure where you have primary tensor descendants.
Oh yeah, I'm
And
throwing
then
away
the
the descendants. I'm
primary
just looking at
is
the h
the
primary.
area part.
I'm looking at h primary here.
I'm
H
writing the full.
Okay, there's a tensor h descendant everywhere. It just kind of goes along for the ride. The point is that I'm pulling out an approximate tensor product structure inside h primary.
But then once you have that structure, most of these things they
Yeah.
make the same.
Yeah, exactly. Exactly. I'm just kind of putting it on a very clear basis, which is something I have never seen before. In fact, like this thing with the Bayes theorem, I would I spent some time studying, looking for it in the quantum thermodynamic literature. I can't find it. Something so simple, must have been done before. I can't find it. Yeah.
Let me ask something. I think Shiraz already asked it, but let me try to ask it just so I understand. Okay, I mean, where does all this Harlow fancy stuff come? Okay, I have the Thermophile double, and it has primary times primary and descendants and all that. Right? And then I trace over one side and I compute the entropy, and you have a lot of states because of Cardi, and that gives you the area. I mean,
Yeah.
can I just say that much?
If you care about calculating entanglement, I have had no ability to calculate entanglement
Okay,
for
I'm
you.
not taking anything away. I'm just trying
No,
to
no,
understand.
being clear about what the
There's more structure. Explain that to me. Sorry, slowly.
yeah the most structure is that you get this approximate, the leading part of the entanglement comes from this expectation value of this linear operator, okay, as long as some nonlinear constraint on the state is satisfied, which is a semi-classicality constraint, okay.
No, but I mean the formula is expressing the entanglement of a full state as a piece and a piece, right?
Yeah,
That was the Harlow's condition.
yeah, exactly.
It was this piece which was the chi contribution, and then this piece which is the code subspace. There was this code subspace structure
Yeah.
and all that, right?
Yeah,
So that all that is being somehow seen here.
yeah, but in an approximate setting, which is what I care about.
The dumb relativist would just say
Cross H bin. I think alpha is bin, right?
Alpha is the bin number, yes. H alpha is like L2 of R. It's like just H alpha is just like it's more like a wave function on a line.
H alpha is a Hilbert space.
Yeah, which is like a set of wave functions on a line.
What is H bin?
H bin is the set of Hilbert space of the states inside a specific bin.
I would just counted that
Hilbert space in the bin, and H alpha is
The bin number.
separated it. Okay.
Just from the point of view of a boundary person exciting low energy degrees of freedom. So that's like these boundary diagrams, let's say. And then in the full Hilbert space, the entanglement, which is the left hand side, is being produced by the area and then this extra perturbation where what these code excitations are. I mean, kind of minor excitations on top of this main entanglement.
And what was that additional piece? So this piece, now I understand the area. What were the other terms?
This is the Shannon entropy from
Some number.
yeah, the uncertainty over the bin, over the area.
Okay.
This is the entanglement of the boundary gravitons.
Okay.
These corrections get big when you have non-semi-classical states or you have bad binnings.
So, is your claim that, I thought that on the gravity side we understood pretty much what was going on. You had a Thermophile double, and you had all states, descendants, weighted by the energy, blah blah. And
Let me say something. Let me say something that on the gravity side, which we don't completely understand. Okay, which is I give you there's a fixed holographic CFT, fixed central charge, the spectrum on the boundary is discrete. The modular Hamiltonian has a discrete spectrum, but it looks like at leading topology the area has a continuous spectrum, right. So, now this is what this formula is. How do you get a continuous spectrum out of a discrete spectrum? Well, you need semi-classicality, and when you have semi-classicality, you have an approximate. You can write down an operator that an approximate operator, sorry, an operator that has a continuous spectrum.
I agree with you. You've done. Please
Yeah.
don't mind. I'm not taking.
No,
any-
I am not
but
taking.
I could phrase the question you just asked as a general question in statistical mechanics. When you get a continuously varying entropy, given that your spectrum is continuous, if it's sufficiently packed, you get a continuous spectrum.
I agree. Yeah.
And so I'm just saying, okay, that's a question. No, what's the connection? What's the deep connection with Harlow? There is some deep. I'm just trying to understand that.
For me, it was a jumping off point. For me, Harlow was a jumping off point. I was like, oh, I will just write down a code, see what happens.
So the code is the fact that is the thermofield double in a sense is the analog of the code. It's left, cross, left, right, same primaries.
Yeah. It's likely.
That is integrated.
Yeah.
You could say is that now that you in high dimension, if you want to kind of see this formula, you would have some thermophile double state, and let's say you have some bulk excitations, right? And then that's some state in the full CFT Hilbert space. And the point of this formula is that the entanglement in that full state is this area term plus the entanglement of the bulk excitations, right? Now, if you want to kind of do this in 3 dimensions, what would be the role played by various things? So here, the bulk excitations role is being played by the boundary gravity. Right?
Yeah.
So in that sense, that would make it exactly equivalent, right? If you ignore these correction pieces,
Yeah.
then it is exactly the same formula.
You could also have bulk excitations of low-lying primaries. I mean, gravity.
In fact, that there is an order 1 correction associated to that, which I was hoping to sweep under. I will sweep it under the rug. There is an order 1 correction, but it's a state independent correction.
I think that has to do with this what he said in the beginning, where
It gets it's an order 1. The point is that in each of these alpha states, right, the low-lying the light fields are in some Hartlocking state, and you have to subtract off their entanglement from log n alpha. So it's actually a small correction to log n alpha, which you have to do. I just swept it under the rug for this talk. The low-lying primaries cannot be excited to any other state, which is what's important. If you allow low-lying light fields to be excited to other states, then you will have to do Susskind-Ulam, which I have not done.
Other states meaning?
Like right now, no matter what the alpha is, the light fields are in Hartlocking state. Okay, they don't care about boundary graviton. They don't couple at all, really. And so they're in a fixed state. They have fixed entanglement entropy, which you have to subtract off from log n alpha.
But you're not allowing waves to move around in the bulk.
Yeah. Because I'm not. My code subspace has only stress tensor insertions. Yeah, and yeah, that's right.
What's confusing me is that, I mean, okay, your area term has the interpretation of arising due to post grading, right? I
Yeah.
don't think that was the underlying reason for the Harlow area term.
Yeah,
I thought it was closer in spirit to what the words you used when you set it up, which was there's a there are set of low energy degrees of freedom and high energy degrees of freedom.
yeah.
There's the high energy degrees of freedom which
Yeah.
simple gravitons don't.
You can. That's exactly right. And so, like for example, if you open the paper by Almeri, Dong, and Swingle, who first wrote down area operators, this is the sort of codes they take. But what I believe is that you can write down an exact area operator there, but exact error correction is just not what is there in ADS-CFT. Okay, it's approximate error correction, and I'm kind of like rediscovering approximate error correction in some sense via coarse graining. And so, even in those codes, you will do some coarse graining, have some amount of approximateness in your error correction, which is not visible in Harlow's formalism. Okay. Yeah.
So, Sandeep, I mean, the way I would kind of try to and then there is this extra high energy degrees of freedom in which this chi lives, and that's what produces the area and so on. But for that theorem itself, it was not important that that's large, this small, and so on, right? What was important is having this direct product structure. And I think what he did can be understood as imparting an approximate direct product structure and sum of such terms in the vector. And once you have that, then that's possible.
How did Ronak get an approximate direct product? I didn't understand.
So here,
Got some course
I didn't want to write what he wrote.
Descendant stems.
Yeah, some more alpha.
The descendants are not like they're just playing around for right.
Primary.
It's more that you're splitting up the primary into like something.
But that's a sum. Sum structure.
No, you can take a direct sum piece and think of it. No, but the descendant is not the chi alpha. The descendant part is not the chi alpha part. It's like that's B1.
This one, no, this part. Yeah,
This
that's
part,
the
yeah.
code subspace.
But
The chi alpha part is this one.
the point is that the chi alpha part is a particular part of that one, where you kind of write H primary.
Yeah, so see,
This is the crucial equation here.
So you have this, usually the structure of, I mean, very schematically, the CFT would be like this. These are primaries, and on top of that you have descendants, right? Now to begin with, there is this structure, H primary but times H descendant. But what was crucial was not just that, but rather there was, H B1, H B2, and then there is some more alpha also.
Yeah, and the
Right?
so
So this alpha was also, he wanted that.
yeah.
So here you could take this guy and take this guy, discrete binning, right? And if you do discrete binning, roughly speaking, what would happen? This would look like, that you have these now bins, right? And in that bin there is this n alpha, which is and then this, which is the descendant. So you have, for each bin, you have this direct product structure, right? And then in this direction lives area, and in this direction lives the H code.
Yeah.
And this is your probability,
Yeah.
right?
Yeah. You just to say this is exactly what this equation says.
Sorry, and when you say coarse graining, you're still measuring actually, you're still computing entanglement entropy between left and right, just on a certain class of states, right?
Yeah.
Restricted to some states, you're not computing a coarse grained entanglement entropy, a coarse grained entropy like we do in a area of a black hole increase.
Yeah, that's right. Which is I mentioned this earlier. I think that these are different types of coarse graining. Yeah.
Does something go bad at beta equals 2 pi?
You hit you log n alpha for alpha less than c over 12 is 0, and basically at beta less greater than 2 pi, the dominant alpha is like in that regime.
Does the semi-classical condition break down?
At beta equals 2 pi, I'm sure it does. Like anything, I suspect anywhere, any situation in which you're stuck here, your semi-classical thing is just nonsense.
Why does it break down at beta? I mean, microcanonically, there's nothing special about beta equals 2 pi.
Microcanonically doesn't.
It's just a Hawking page transition kind of thing, right?
Yeah.
No, sorry, I meant the Tomo field double state at beta equals 2 pi. Not that.
Yeah.
Meaning the one that is not dominant.
At beta, at the transition point, it has to. It's probably some complicated combination of all three phases.
But even that, I mean, it's not locally unstable. If you take temperature lower than whatever 1 over 2 pi, it's locally stable. It's just like some first order phase transition to the.
But the area, would the area operator still be semi-classical?
I would imagine that is just about.
Yeah, you're saying it's just a sum. Maybe. I would have to check. You're just actually the thing I get confused because of this intermediate regime where I don't know what happens.
We can look at beta as a label for the state, right? Label by energy instead.
Yeah.
Something special is happening as you change the energy through that. So I don't take any specific change.
Okay.
But it is semi-classical, you mean whether the area would be large, order C, right?
It will.
No, but if you go there, then it's not, right?
Where?
If you go very low in energy.
Yeah, you have to go to energy of order 1.
No, I mean less than C by 12 you said, no?
No.
So
Oh yeah, that's 1. That's the gap. That's the gap.
Yeah.
C by 12 is order 1.
Because we normally measure that from minus C by 12. That's 0.
No, it's still not order 1, right? It could be C by 24.
What?
The gap could be C by 24. It is not order 1 necessarily. It's still less than that.
Anything above the black hole gap will be fine.
But
Well,
you could have
above CO,
energy
not
of order C and still not.
No, but what I mean is you need to have the black hole density of states.
Yeah.
But that's all.
yeah. Mm-hmm.
So, let me just go back. I was just trying to understand the connection. Okay, so I see what Abhijit was saying. I think that's why I thought you were saying something else. I was a bit confused. But if that's the point, okay, then we just say that, okay, there is some entanglement. In this sense, there is a tensor product structure. In the sense of descendants times.
Yeah.
And then we say, okay, we separate and the code subspace is the descendants, is the boundary gravitons.
It's messing with the descendants and messing with all the primaries within a bin together.
Why do you? I mean, why do I do that? I just
And
say
I
the code
just-
subspace is the descendants. Then.
No, but the code subspace is not just the descendants. You can like change the you can change the probability of various primaries. You can like as long like the
You can change the probabilities for different states.
with different bins, The idea is that in the semi-classical regime, you can kind of mess with like which bin is dominant. Okay, but what you can't change is the fact that you have a microcanonical ensemble within each bin.
Right. But I mean, okay, we think about code subspaces and all that given a state, right? Given a state, and then you say, okay, what are the errors?
But here the code subspace is slightly weirder because it's not a linear state. It's not a linear space, right?
Okay, what I'm saying is, given the P's, given the POs, right?
Yeah.
Now let's say we've been given a state
Yeah.
specified in terms of the POs, and now you build various kinds of descendants on
Yeah.
it, into which you encode
Yeah.
information.
Yeah.
Right? So in that sense, the code subspace is the boundary.
That's what I was also thinking.
Yeah.
That's what Abhijit was saying.
The code operators are boundary graviton operators, but sorry.
I mean, he was saying, I think if you do like terrible changes, then it might end up changing the
Yeah,
distribution that you have.
It might, but that's the
Let's say you
spirit
do a
of
little bit, yeah.
then you destroy the black hole or you change.
No,
it
but
into a completely different
my code subspace allows that, right? My code subspace allows you to like there's an operator in my code subspace which projects onto factorized state.
subspace is bigger.
And my code subspace is ridiculously big. But the point is that this approximate code subspace I ended up with sticks within the semi-classical regime.
But that's what Sandeep was saying, right?
That's kind of like what you were saying, yeah.
Say again.
But
He ended up getting a result about the setting that you have.
yeah, where you are allowed to mess with the probability of various bins of primaries, okay, but not allowed to like mess with what's happening inside each bin.
Because your approximation worked for the case
Yeah.
where drastic changes were not
Yeah, exactly.
right? So in the end, when you got your result, it's basically that you have some notion of the POs, which you won't change too drastically.
Yeah.
And then your boundary gravity.
No, not too drastically, but like you can like move the peak by an order C amount. Okay, it's just that you cannot change the derivatives by an order C amount. You cannot change the width.
Move meaning you can consider another state.
You can
Like
consider
There is an operator which you, yeah, which it's like e to the minus beta minus beta prime h, okay, which takes a semi-classical TFD, gives you a different semi-classical TFD, right? But it's still semi-classical. So you can change the POs quite drastically. You just can't make them oscillate.
This includes black holes of different masses.
Yeah,
sorry,
You
but
change from one to the other.
yeah.
but the result that you get
It's good enough to account for that.
That area was actually dependent on PO, right?
Yeah.
So in that sense, the code subspace was not doing much.
The code subspace is not doing much here.
Yeah, because in Harlow's case, changing the code, that chi alpha was unchanged.
Yeah, the analog of the chi alpha for me is that within each of these guys, there's a microcanonically entangled TFD.
Yeah,
Okay, that's the chi alpha for me.
That's log n alpha, right?
Yeah.
That's how you get log n alpha.
That's right.
Yeah, but that P alpha was also could not be changed.
P alpha could be changed. P alpha could be changed. You can. In Harlow's case, projector onto alpha is in the algebra. And in fact, this is what when you calculate any entropies, this famous Akers-Rath paper is all about that.
Yeah, but I mean, what is the so I also want to ask along the lines of Abhijit. So there was a piece coming in Harlow from the chi's, right? The chi alpha, which was not changing. You change your code subspace states.
Yeah.
And what is the analog of
So
that?
the fact is, the analog is that my H primary has this H primary alphas, and within each H primary alpha you have a microcanonically entangled TFD. Okay, those are the chi alphas. But you can change the relative weighting of the.
That should be the maximally entangled state. Let's say
Yeah.
n alpha degrees of n
Yeah.
alpha.
Yeah, basically, yeah.
Giving you, but
It's-
that should have log n alpha.
Yeah. It's well, it's not maximally entangled. It's like entangled with the nice smooth envelope function, but close enough.
Yeah.
Okay.
Oh, explain this from an edge. This is primary, the Hilbert space of primaries. Is that?
Yeah, it's
No
the Hilbert.
descendants.
Yeah, it's the Hilbert space of primaries.
And that's the direct sum over various bins.
Yeah,
Is that
yeah.
what I mean?
And
that the primary has some amplitude to
Yeah.
lie in some way.
yeah. So you should really think of this as an approximate equality here, because if the bins were non-overlapping, it would be a direct sum. But I will think of it as a. In fact, what I will do next is make this approximateness precise. But so within each bin, you always have a microcanonically entangled TFD. Okay, there's a bin on the left and right.
Should I just explain that? Because within each bin, you just have each operator has the same
Yeah.
possibility,
Ah.
and it's microcanonically entangled left and right.
Yes.
So when
Yeah, that's right. There's a bin on the left, bin on the right. These two are microcanonically entangled.
And roughly the same weight, so
Yeah.
you log n alpha.
Yeah, exactly. So and those microcanonically entangled TFDs are my chi alphas. Okay, but I'm allowed to change the relative weighting of the chi alphas. Okay.
now I understand better.
Okay, what I'm going to say next, I think, has been partly covered by the discussion, but I want to be explicit, because this is where I try to make the approximateness precise. So what I'll do next is I'll define an H bulk. Okay, just come completely out of nowhere. I'm just like pulling it out. I'm going to define it as basically here you go. Basically a function of alpha. The functions of alpha tensor H descendant. Okay. So this is kind of like the naive bulk description of the Hilbert space, where basically I have some so alpha for me is the area, okay, and I have some wave function over the area, and I can have some boundary gravitons which depend on alpha. Okay, so here the entanglement entropy we expect it to be just exactly expectation value of d alpha. Now I am forgetting about what's happening below the Hawking page. So d mu alpha is just d alpha. D alpha S1 P alpha log the projector onto each alpha expectation value plus H alpha plus what do I say, integral d alpha P alpha S rho alpha, right? So
S1 P alpha was this log n alpha?
yeah. Log S1 P alpha is the log n alpha, yeah. Okay.
What is this notation psi alpha?
It's the set of wave functions on alpha. Alpha is like goes from c by 12 to infinity, or sorry, c by 6 to infinity, or some large cutoff.
Some probability distribution on alpha?
It's a wave function. Wave functions are square roots of probabilities.
Winning parameter.
No, I just kind of I change things upon you. Okay.
So what alpha is?
Now alpha is just now I'm just defining a completely different Hilbert space, where alpha is just like a basis. Okay, This is completely different.
Okay, but basis of primaries or what?
Bins of primaries.
Yeah, like it's a basis of areas. Okay, like the bulk Hilbert space should have a description like this.
Basis of primaries of bins. You mean your one bin?
No, it's no. It's not a basis of bins. It's a basis of areas. It's a bulk Hilbert space.
Rows out of your bins, right?
It will. You have to give me one more step to make the bin. Okay. Right now, it's a bulk Hilbert space, not a core Hilbert space.
So what does that mean? I don't know. You haven't quantized the bulk. Oh,
I have I have quantized the bulk here. Like you get this from quantizing Chern-Simons theory and stuff. The Virasor.
Okay, so now this is different from what you've done.
Yes.
So
Now you're in the bulk and you've done some bulk.
Yeah. And just because.
you take Chern-Simons theory, okay, then what do you do with it?
It's the Hilbert space on a cylinder, okay, contains two zero modes, which are m plus j and m minus j, and boundary gravitons. That's it. Okay, it's indexed by these things, and I have forgotten about j, so for me that's just a alpha.
Alpha is like m.
So it's M.
I will interpret it as area rather than m. There's a small difference. Yeah. Mass. Yeah, but I will call it area because and I will put in Wheeler-DeWitt wave functions that are fixed area ones, not fixed energy ones.
So in no way it depends on your f of alpha.
Right? Yeah. H bulk is just a completely different thing. Okay. Now the question of what do you say? The question of ADS-CFT is how the hell is H bulk inside H-CFT tensor 2? Okay. And so for this you need a map. Okay. And so you need a what do you say? Okay. This is called a holographic map. Okay.
By the way, okay, just so I understand, you're taking pure Chern-Simons theory?
It's pure Chern-Simons, yeah, because there's no batter.
So it's not really dual to CFT.
It's not dual to a CFT. It is a
What is the precise question? Sorry.
huh?
Okay, so it's not dual to a CFT, but you're saying, so you said the question of ADS-CFT is how is the bulk Hilbert space embedded in this?
There's a sector of the bulk Hilbert space
Okay.
without any matter excitations. Okay.
How is that embedded in this?
Yeah. Yeah. Okay. It's not the question of ADS-CFT, but it's a nice way to pose ADS-CFT as a Hamiltonian question. You want an operator. Okay. And basically, what do you say? What all of this suggests is that you can define V of f acting on some alpha equals 1 by square root n alpha sum over O square root f alpha of O e to the I phi alpha of O. Okay. Right. And its identity on the descendant factor. Okay. So it
Is the map VF acting on
because it depends on f. So let me just forget about this. So V depends on f and these extra phases. Okay. Yeah. Now the point is that under this map, I reproduce exactly the non-corrections part of this story. Okay.
Let me understand that equation. So alpha is the bulk wave function for given masses, or
Yeah, yeah.
or it's an
Yeah.
eigenstate of
Alpha ket is an area eigenstate. That's right.
is the area eigenstate, and this is being mapped to the CFT through V
Yeah.
as and 0 0 there is the CFT ground state.
No, O is primary O left, primary O right.
Primary O left. So okay, sum over all primaries
Hmm.
and some phase which depends on
O and alpha. Okay. You can jigger around. I currently have multiple different possibilities for what properties the phase function can have, and it gives you different properties. So I'm not entirely. This is not like the final proposal yet, but any proposal of this form will reproduce this thing. Okay.
and the F alphas are up to us. They are your winning.
They're the binning function. So they are
So this map has some, you can choose different binning functions.
Yeah, and like for each binning function and each phase function, there's a different map.
He's going to produce that formula from that.
From that
so
formula,
that
but-
F appears there. So
Yeah, exactly.
No, I get that, but I mean, in general, we expect some unique map, right?
Yeah, maybe it's unique.
If the area operator is a well-defined object in the CFT, then its eigenstates should map in some well.
The area operator is mapping well. Yeah, here the area operator, well.
I don't know how the area operator is defined in the bulk theory, in canonical quantization of gravity.
You define it as.
I know how to define the mass, if that's what you want to do.
No, you can do fixed
Can you
area.
define the area? I
Yes,
don't
you
know.
can. Yeah, you can. You calculate the Wheeler-DeWitt wave function in the fixed area basis.
I
And
don't quite know what that is. Okay, anyway, explain.
yeah,
it to me. I know
on the Cauchy slice, you put a condition that at the extremal surface the area is some number. Okay, so the area and yeah, that whenever you put that and then you expand your wave function in that basis and then integrate the mod square of the wave function with the value of the area.
But also, just at the level of the phase space of gravity, the area is some function.
Yeah, exactly.
All the other phase spaces.
Exactly, it's a gauge invariant function.
But
So
it's an ambiguous function when you go to the proper quantum theory. You have to do, because it's got non-linear.
operator,
yeah, but those are order G Newton. Those are order G
Anyway,
Newton.
go ahead.
Those are order G Newton.
Okay.
Like you're right, of course, that
Okay.
yeah. So in this setup with Chern-Simons, there is a simple way to quantize it. Okay, because there's no local bulk degrees of freedom. But once you add local bulk degrees of freedom, there are order G Newton ambiguities in A over 4 G Newton.
Okay, but let's say there's an area operator, so then you say it must be mapped in a precise way to the CFT.
Yeah.
But then you won't have any, there should be one map, right?
Yeah.
Some f of yours is chosen.
Currently, my area operator on the boundary has an ambiguity, so that same ambiguity is popping up there. The choice of binning function. Okay, and ideally one would want to find more and more consistency conditions to kind of bootstrap a unique map. Okay, but we don't have. I don't currently have enough consistency conditions to say much.
I understand.
Okay.
You're saying there should be such a f,
Yeah.
and then you recover.
Yeah. So let me tell you some nice things that this does.
Sorry, where is the information of phi in S entanglement?
It's not. It cancels out because when you look at density matrices, the phi's go away.
Since binning is a reasonable thing to do only when there are lots of states, this is presumably tied to the large element.
It is tied to the large limit. Yes.
So it's too fundamentalistic to expect really an exact area operator.
No, that's what I mean. Yeah, it's some
Yeah.
approximate thing.
So maybe there are approximations on both sides, and to the extent.
Yeah, but I am
It's
interested.
some
I am interested in finding this in a fixed large C CFT, fixed C,
Fixed C.
fixed but large C. Okay, and then the question is, okay, maybe the answer is that it doesn't exist, and that would be interesting on its own.
Maybe then there are many things you can define because you are choosing some smearing function.
Yeah,
I mean, when you're looking at water,
Yeah.
if Avogadro's number is large, it's
Yeah.
reasonable to look at some density function.
yeah.
If there are 10 molecules, it's ridiculous to do it.
Yeah, agreed. Yeah, it fixed but large C, and the question is how rigid is ADCFT, right? Like if it's so rigid that I have enough consistency conditions to fix all these things by staring at the one loop corrections to the gravitational calculation or something, that would be interesting on its own. If it's not, that is like the null hypothesis that you can have that there is some ambiguity here.
But strictly in the large C limit, you expect F alpha to be something.
No,
I think it's
strictly in the large.
different F alphas will differ only in subleading orders.
Yeah, strictly.
See, that makes more sense.
Yeah, I agree completely.
The whole choice of f's and
Hey,
then some approximate area operator.
These are order 1 ambiguities. These are. That's what I keep saying.
Order 1 will change the area operator by order 1. Right?
Yeah,
Order 1, but not order C.
yeah. Or order C and log C are
So why
universal.
not order C also?
Well,
F alpha there.
if you try to make F alpha so weird that it messes with the order C piece, then the corrections will become big.
Make F alpha twice the width. N alpha will go to twice N alpha. Log N alpha will get an additional correction by log.
Yeah. Because yeah, that's right. And this is why it's important that by the way, yesterday we were discussing whether this formula works for any entropies. It does not, and it's quite important that it doesn't quite work for any entropy. Yeah.
I see.
Yeah.
So
So these are order 1 ambiguities. Of course, yeah, I agree that it's not super surprising if it turns out it's impossible to fix the order 1 ambiguities.
Or there are many choices.
Yeah, that's what I just
Choice
said.
here, choice here, you try to match.
That's what I just, isn't that what I just said? It's different?
Fix, okay. I thought
Not possible to fix.
okay.
That means that there are many choices, right?
But
Oh,
sorry.
yeah.
So the claim here is that a fixed area state
Mm-hmm.
on the gravity side should be thought of as some state vectors.
Yes.
on the same.
Yeah. Okay, let me give you a little bit of evidence for this. So,
And you would say something about what the f's you already told us should be some, suitably smooth smearing function
Yeah.
of the scale of the
order 1 width.
order 1 width, and the phi's, anything depends much on phi? They are random variables or on the
I kind of want to take them order 1 variation in alpha and basically more or less random in O, because when I sum over O with these phases, you get exponentially small corrections. It's exactly where I expect corrections to the semi-classical limit. Okay.
And it's true that these states are eigenstates of your area.
Yeah. That's because that's what
More or
this.
less,
Yeah, exactly. It's true. And so one thing, for example, is that you can take the thermofield double, a gravity calculation. Okay. Do a fixed. Calculate the Wheeler-DeWitt wave function for fixed area. Okay. This is going to turn out to be e to the e to the a by 8g e minus beta e of a. Okay. This it's half of the entropy, square root of the entropy, square root of e to the entropy, and so you take e to the a by 8g.
Just say again, what is this calculation?
So this is just the Wheeler-DeWitt wave function calculation in the fixed area basis. Okay, so you're fixing the area here, but the area is conjugate to the opening angle, so the opening angle is unfixed, and then everything else I think you have to. The simplest thing to do is take k equals 0 everywhere. The extrinsic curvature equals 0 everywhere else. Okay, minus beta e of a. When you do this, and again I'll rename this alphas. It's a semi-classical calculation. Yeah, so I'm pulling out the wave function from there, putting it here, integral. I get basically exactly what do you say? 1 e to the minus s over 2, e to the minus beta e, beta by 2e. Oh, OO. Okay, so you get exactly a thermofield double if you plug in the semi-classical thermofield double wave function in the fixed area basis. You get a thermofield double via this holographic map. Okay, up to some corrections, which in this case
Sorry, so on the left-hand side you have
I put in the wave function
wave function.
of in the fixed area basis of the thermofield double.
And then what is the V? V is
No,
the
V is that map.
but what do you actually do?
I mean,
so
it's
you compute this, you have the wave function.
V goes through axon alpha.
Okay.
You get this entire mess here.
Oh, that by just definition.
Yeah,
Okay.
yeah, and then you just do the alpha integral, and then it kind of works out. Okay, I'm just kind of trying to spare you the details.
I thought you were going to take the phases will oscillate unless you take inner products or something.
No, the phases kind of when you integrate alpha over an order 1 width, the phases don't do much. The phases are important when you sum over O, because in an order 1 width there are exponentially many O's. Okay, so that's when these phases are important. These phases for when you integrate over alpha, they're not interesting. Okay, anyway, you can quantify the corrections.
Because you integrated over alpha, the O dependence of the phase goes away. Then
Yeah.
you don't do much.
Yeah, exactly. Yeah. So anyway, so you just get this, and this is this. The point is that this is exactly what you expect a holographic map acting on fixed area states to do. Okay. Similarly, you can argue that you can do the coarse graining using V dagger.
Because you get e to the minus
This is the thermofield double.
the thermofield double.
The thermofield double should give you the thermofield double. So everything seems to be working out. Okay. Yeah.
Is there a reason you said you insisted that you wanted to talk about the area as opposed to the energy? What was
So if I put a fixed energy basis, I get a 4 here, not an 8, and then I'll get the wrong factor here. So so the point is that basically this map only works for the fixed area basis, not the fixed energy basis. This is nicely explained in Zhenbin Yang's paper in 2018. Like, yeah.
So when you write OL, what is happening with the descendants? Are they entangled or not?
The descendants, they go along for the ride. Like it's just acting as an
It's the module by module product.
Yeah, you can think of it as a model. Like the V just acts as identity on H descendant. Okay, and yeah, so and if you I haven't done this part of the calculation carefully, but I think you'll just get like a fixed, basically the state of the descendants in a particular module only depend on the primary energy, because in the thermophile double, right? So I think it'll just work out.
No, but here even in the descendants in the thermophile double you will get entangled, right?
Yeah, that you'll get. You have to put that in here also. When I'm only focusing on the alpha sector, the descendant sector will also be entangled. Okay, and they'll be entangled by like square root of an eta function or something like that, and that same square root it will work out. I haven't like done the calculation super explicitly yet, but I'm pretty sure it works out. It's not doing anything interesting. Yeah. So anyway, so this is the. Is there anything else I want to mention?
So the punchline here is that the area operator in the bulk can be mapped. But I mean, okay, so I understand the area of calculation, but the punchline was that you can map it to the boundary like this. Right?
Yeah, and like you can basically get this coarse graining story. When you write it in Hamiltonian language, is like a sort of holographic map, where you take a fixed area and like give it, give a bin.
How did that punchline emerge from? So you did from the fact that when you move your V, something about F alphas was used to get it to work, or
the fact that integral sum over O F alpha was n alpha, that was used.
sum over F alpha O. Huh?
Sum over O at fixed alpha is n alpha, that's used. Yeah.
What is O?
O.
Oh, sum over.
Yeah. Yeah. And also the integral over alpha is 1 and all that. It's yeah.
So
Yeah.
So the bottom line is that.
So yeah, maybe I'll just summarize what's happened till now. Okay, so what I did now basically was that Harlow gave us a framework to think about the area operator. I decided to apply it to a concrete code subspace in 2D CFT. Got that the information theoretic area was 0, and we diagnosed it by the code being dumb, but we stuck with the dumb code. Okay, and did the explicit coarse graining to get this area operator that works on a set of states not closed under linear superposition. So there's a semi-classicality constraint that has the property of semi-classicality that is required. Okay, it might not be the semi-classicality constraint, maybe there's a better one, but it's better than any obvious thing I would have written down. Okay, and then then basically you can argue that you can get this same behavior by taking the bulk Hilbert space. Again, there's no local degrees of freedom, so it's very easy to write this stuff down. Okay, and just mapping it via some fairly straightforward holographic map. Okay, one cool thing by the way about this holographic map. Okay, the fact that there's only one alpha, the fact that the left and right ADM energies agree, is actually a gauge constraint in the bulk. Okay, it's gauge, but it's a code constraint in the boundary. It's a code constraint, not a gauge constraint. You know, there's this cool thing that Harlow's paper, the area operator kind of looks like a a particular term in a non-abelian gauge theory. But like it's very hard to make that work. People have been studying gravitational phase spaces for years, trying to say something about it, and it never quite gets there, or even close really. And maybe my suggestion is that like it's like an it's like some sort of emergent gauge constraint that's coming from the codiness of it all. Okay, yeah. So anyway, you do this, and then you calculate the entanglement of the what do you say, and then the
statement that smooth gravitational backgrounds have this kind of constraint?
yeah, that's the idea. Yeah, that's the idea.
What was the constraint again?
That my primaries agree, which is also the constraint. But yeah, and finally the point is that this area operator, when you pull it through via this holographic map, seems to give you exactly this guy.
But
The
you
area.
violated that constraint by putting insertions in the Euclidean past.
Yeah, so it's a gauge constraint in pure GR. Okay, which is a code constraint with the code without new primaries.
Yeah.
Okay, yeah, good. So yeah, it matches like.
Even if you did that, the marks would have to agree, right?
No, the masses of the left and right won't agree. Yeah, basically because the new operator is like dressed to either the left or the right, and that dressing gives you extra mass on wherever you put it. Okay, yeah, so you can kind of reproduce this approximate area operator by the obvious sort of, this is what I would call the Jeffreys-Kolchmeyer type area operator pulled through this holographic map. Okay. So this operator, right? It is not coming from any entanglement calculation in the bulk. Okay, it's just something that Jeffreys and Kolchmeyer noted that you can put. Okay, and that's like the area term is like, this is the fact that gravity knows about the entropy, but not the actual microstates. The fact that you can write down an area operator, but you cannot prove it has anything to do with microstates.
What was even that line, the first line? What is that?
It's a projector onto alpha in the Hilbert space, with log of S1 P alpha, which is like my N alpha or whatever. Yeah, so it's just it's like
What is S1P alpha as per the underlying bulk Hilbert space?
nothing. It's just some fact about the semigroup the quantum semigroup symmetry of 3D gravity. It's just some yeah. It really has no obvious meaning in the bulk Hilbert space, this term. Okay, this is what Jeffreys and Kolchmeyer noticed, that the area term has no, and people knew it, but like Jeffreys and Kolchmeyer were very sharp that the area term has no clear meaning in the bulk. It's just something you put in. Okay, and yeah, so in fact, and then Pennington and Witten also argued that if you have pure GR, there is no unique area term. Like there's a consistent extension where different area terms could give you different entropies. Okay, and for them it's fixed only by the addition of bulk matter. But here you just put it in, okay, from whatever considerations, and it matches to the actual area term you get in the actual CFT via the holographic map. Okay. Now, the nice thing to do would be to go the other way.
And that S1P alpha turns out to be related to.
Yeah, log N alpha is just log S1P alpha. Yeah. So, like in some sense, this defect operator, this area, or it's called a defect operator sometimes, is kind of this pulled the other way through the holographic map. Okay, more precisely. And yeah, so that's the upshot. Cool. I think that's all. Like I could say something on multi boundaries, but I'll decide what I'll talk about tomorrow. Either I'll continue into multi boundaries, and you guys, or we can talk about something completely unrelated. I don't know.
Thank you.
Yeah.
But let me just ask you, and then we
Yeah.
can continue later. I mean, to the extent that some of the thrust is, okay, Harlow identifies the analog of the area through this guy alpha entropy. The thrust is to now try and understand that area operator in a precise way in the ADS CFT map.
Yeah, try
There is
it.
a semi-classical notion of area, of course,
Yeah.
in the bulk, And is it a precise concept in the CFT or is it an approximate?
Yeah.
That is one
And
of
like
the
kind of index all the approximations and all the ambiguities, you know. That's kind of, yeah, and that's what I hope this has done. And there are concrete checks, like I do the, you know, doing the one loop calculation in the bulk, not via Maloney-Witten, which assume that one loop equals descendant, and seeing whether the gravitational calculation gives you something extra beyond Maloney-Witten or not. And that's, yeah.
I see. And just to ask, because Harlow could have been used even in this for a single boundary case where the area is the RT surface, the idea would be again that RT surface area also should have a precise map in the boundary.
In fact, that's where I started, and if you guys are interested, I can talk about that tomorrow. Yeah, because you can do it, and there also again you run into this like you end up running into the need for coarse graining, okay, and but there is not as sharp the need for coarse graining, but there is a small subtlety that I am confused about with the cutting up a circle into multiple intervals. But there are some very interesting mathematical structures. So, you know, some old papers of Gabardiel solved a lot of stuff. Yeah.
When you say more than Maloney-Witten, you mean the one loop correction comes
So in Maloney-Witten they say the
the zero mode contribution?
no, the one loop correction maybe zero mode. Also in Maloney-Witten they say just end up saying that one loop corrections are the descendant contributions, and they write an eta function. Okay, and like the point is that now I am motivated to go back and re-examine whether that is exactly correct or not. Maybe there is something they missed, and there's something beyond the descendants which would be these ambiguities, or maybe this.
What exactly did you have in mind?
I don't know. I have to. I haven't started doing this yet, but it's something I think is something I will do.
One thing is that there's a zero mode and it has quantum fluctuations, so that will give some kind
Is that right?
Tied to the mass.
Tied to the mass, yeah.
That would be sensible. Yeah. Somehow that the one loop also knows about fluctuations of zero mode or something. Yeah.
Roughly that's what you have.
That's what I would have think. Yeah.
Maloney-Witten is an Euclidean space, and they transform the black hole.
I'm talking about the one loop part, not about the S transforms.
No, but that's also what I'm talking about. They transform the black hole to the ADS vacuum, and then there's no zero mode for us, right?
Right. So that's only the descendant part of the one loop. And then I was imagining that there's also a contribution coming from.
Maybe, yeah.
So then that will go going from being finite temperature to finite mass or something like that. I mean, because this is supposed to be exact.
Yeah.
You take the partition function at finite temperature.
Yes.
The fact that you can view this as space and that as time is an exact thing.
Yes.
And then you don't expect a mass thing.
Yes.
Yeah. So.
I mean,
if I just stick to the black
Yeah.
Yeah.
for a moment.
Yeah.
There are the descendants, which are the sort of the variable modules. And then there is also the zero mode, right? The mass.
Yeah. But with the Euclidean black hole.
Yeah, sure. You could.
So we're fixing temperature, then mass doesn't fluctuate.
Why not?
Because
There's a wave function for the mass, right? At a given temperature.
Yeah, sure.
I mean, say classically, there's a mass is fixed
At one loop, it should fluctuate.
No, but there are no degrees of freedom in ADS, I think. All degrees of freedom are the mass.
No, it should be there in the zero mode of the boundary gravitons or something.
I mean, there's L0. I mean, everything that's there has been taken account by the
That's what I'm not clear.
I also think
Yeah,
because that you do once you have the boundary circle size and so on, you do the path integral, and I think it's one loop exact.
It is one. The descendant contribution is one loop exactly.
And you get the entire eta whatever function,
Yeah.
and that's the full answer.
Yeah. So typically like.
That's what I think.
Yeah. So the point is, if I take a thermophile double, right? Okay, then I know that there is some uncertainty in the mass. When I glue two thermophile, glue the cat and the bra, okay, to get the partition function, where is the uncertainty in the mass going? I don't know. Like Maloney-Witten doesn't seem to have a place for it, and I need to re-examine it to see if there's maybe it goes away in some way, or maybe there's some extra thing that you know.
Every fluctuation of the metric can be transferred to the boundary. And the boundary fluctuations are the boundary gravitations. So anything that you think about looks like is a diffeomorphism.
Yeah.
So that's how it works. I mean, technically, now I don't know physics.
No, no, I agree. But okay, I have to. I just need to. Yeah.
I mean, for instance, if you look at the JT gravity analog of this, there's a mass weight function for the mass and the mass fluctuates, but that is accounted for by the Schwartzian.
Yeah, that's right.
It's very similar. It's one loop exact. It's one loop.
But there's something strange, right? See, what they get is a Virasoro character for the one loop, but that Virasoro character also also includes the fluctuation in the primary.
What? No, that's
Because if a change in the mass is a change in the primary,
we work in the dual channels.
that I agree. But
So
like,
we're just doing the Virasoro vacuum. See, that's what makes this calculation tight. Because you do the vacuum character you cannot change the mass a little bit because L minus 1
yeah,
annihilates the vacuum character but not any other mass.
I agree.
It's a very tight structure.
Yeah. Yeah, maybe the subtlety is in the S transform then, like the way that S1P contributes to interpretation.
Exactly. From the S point of view, it's very clear, and then you want to interpret that from your un-S.
Maybe, yeah. Maybe that's where the subtlety is. Yeah, I have, yeah. Which is also the same as Munkar zero mode, I think. Cool.